Hello there. So now we're going to finish up by coming much back closer to home and looking at the role of radio astronomy for studying the solar system. And we're going to start with looking at radio astronomy, looking at the sun and the environments of the sun. So I will confess up front that this is not my area of expertise at all. So I'm really just going to give you a kind of a pictorial overview of some of the ways in which radio astronomy contributes to this field, to give you a flavor of what goes on in that area. So I want to just remind you first of the kind of phenomena that we see on the sun. So in this little movie, you see the sun rotating. The sun rotates about once a month, and you can see the groups of sunspots, which are the signs of magnetic activity on the sun. So these blemishes are where you have a strong vertical magnetic field, and it's usually come in pairs, as you can see. And these are the top one end each of a loop of magnetic plasma that is sticking out of the sun, preventing the convection and therefore cooling the surface a little bit so that it looks darker. So that is what it looks like in the optical. And here is a radio image of the sun. Okay, so this is taken actually with one of the mainstream radio astronomy telescopes, the VLA, that we've seen many examples from over this unit. And again, this is just at a fairly standard frequency of 5 gigahertz. And so you can see the disk of the sun first of all. So that would just be literally the black body radiation from the sun itself. Obviously, the sun's very close, so it's very bright. But you can also see these hotspots, which correspond to the sunspots here. So these are more intense bits of radio emission. Some of these would be free, others would be non-thermal emission from the electrons circling around in the loops of plasma, as we shall see. So again, I just want to remind you of this multi-wavelength view of the sun. So here, a lot of solar phenomena is actually studied at short wavelengths. So the ultraviolet, extreme ultraviolet, and X-ray. So this is extreme ultraviolet imaging from a satellite. So you can see the sun here, and you can already see in this still these loops that are sticking out the side here, coming up from these active regions. So the sunspots would be just at the base of these. And if we play the movie, you can see how time variable and everything is with the sun. So you get these loops with the plasma running around the loops, basically eruptions. You can see coming up here. Yep. So there's a big eruption. So this would be a so-called magnetic reconnection event, which dumps a huge amount of energy and really powers a lot of this activity and powers the whole upper atmosphere of the sun, which is up at millions of degrees. So all of this is powered by magnetic field of the sun, which is very strong and gets very twisted up because of the way the sun rotates differentially and the combination with the convection currents in the outer parts of the sun. All of that churning motion creates a dynamo, creates a strong field, and then twists up the field lines over time, which makes the sun active. So most radio observations of the sun are done with dedicated radio telescopes that only study the sun. They're designed to look at the sun. These are referred to as heliographs. So there's a long history of this. Here is a picture of one of the ones that's done a lot of work in more recent times in Japan. So nothing to do with a big dish in the background. So that's a radio astronomy dish. It's this array of small dishes here. So there's 84 little dishes, each 80 centimeters across, spread out over a half a kilometer baseline. So it's an interferometer. You can see it's very densely packed, okay, interferometer, and this is working again at a fairly sort of standard radio frequency of 17 gigahertz, so in the centimeter regime. And so, you know, the resolution is sufficient here. It's about 10 arcseconds or something like that, to give you quite a lot of detail on the sun, and a lot of, you know, the sun's very bright, so you don't really need big telescopes, at least, you know, to get reasonable detections. So there's a wide variety of emission mechanisms for the sun in terms of radio emission. One of the main ones is what's referred to as gyro-synchrotron. So that differs from the synchrotron that we've learnt about in the unit, which was to do with relativistic electrons spiraling magnetic fields. So gyrosynchrotron, the electrons are lower energy, they're still fast moving, but they would not be relativistic, but they still do the same thing. So they, you know, you've got these loops of magnetic field, and the electrons, whenever they're generated, will spiral around the magnetic field lines and emit radio waves as they do so, as they're accelerated. So we'll see this time and time again. So, you know, this means we should expect to see these big loops from the sun at radio wavelengths, and here's an exact example of that. So the picture on the right is a radio picture. The picture on the left is an X-ray, soft X-ray telescope picture. That's what this means up here. So this is actually you can just see in sort of shadow here, the edge of the sun, and this big loop is sticking out the side. These are enormous sort of structures. You could easily fit the sides of the Earth inside this many times over. And you can see that the radio and the X-ray pictures are very, very similar. So the X-ray is basically, you know, bremsstrahlung emission from the very hot million-degree plasma that is circling around in these loops, and then the radio emission here is that gyrosynchrotron process of the electrons moving around in here, or any ions, but mostly the electrons doing the emitting, moving around the loop and emitting radio waves as it goes. Now, as you saw from the movie just now, the solar magnetic activity is extremely time variable, and every now and again you get a very energetic event, which is referred to as a solar flare. So this is again driven by the magnetic activity, and you know, at the top left here you've got a whole image of the sun at radio wavelengths, and the flare that you can see a time sequence of in the images at the bottom here. So that's how that's varying. But this is, and this is a very fast phenomena. So this is the intensity of the radio emission from the sun, from this solar flare event. And you can see that this is only 30 seconds of data here. And so it's flaring up and down in about 1 second of time. So this is you know, part of the difficulty of studying these kind of phenomena. You need very high time resolution. Okay, so if you want to observe these things in detail, you know, you need sort of sub-second time resolution of your observations. So that's quite a challenge. Also, as you can tell here, you need a massive sort of what's called dynamic range. You know, you might be going from hardly detecting the emission 1 minute or 1 second to the next second you've got an extremely bright patch of emission as well. So that can be quite a challenge to image well both very bright and faint sources at the same time. So just a little bit on this idea of magnetic reconnection. So just the diagram on the right here, just to give you some idea of all the different processes. There's an awful lot of complex physics goes on in these things. So you would start out with a loop down here, But there are occasions when, the magnetic field will get pinched together. And when that happens, you can basically kind of short circuit the magnetic field. And so that this, what used to be in a loop, squeezed together, and it will split into two new loops. One of them will, and you can think of these magnetic field lines, like it says here, as stretched. So there's a lot of tension in the magnetic field lines. Think of it a little bit like an elastic band, is always a good analogy. So we're pinching that together here, and then you get a reconnection, and it will form two new loops. So the material in the lower loop here will form a new loop going this way, and there'll be the tension in the magnetic field lines will pull the material and accelerate it back down towards the surface of the sun, where it will bump into this kind of structure here. But more interestingly is the one that's left up here. And so it will get a massive acceleration outwards. And so material gets ejected from the sun. And so you get these big eruptions, you'll see big loops, and you can see eventually the material will actually get completely ejected into space, as we shall see later. And so later on, we'll see that a lot of fast particle acceleration is going on in here as well, and that's also eventually will contribute to the radio emission as well. But to try and zero in on exactly what's happening in these magnetic reconnection events, it's still not very well understood. So this is sort of complex magnetohydrodynamics going on, and so that actually requires better spatial resolution, high time resolution, and as I said, high dynamic range as well to deal with the varying intensities. And so it's hoped that the SKA, which will obviously be much more sensitive and much higher spatial resolution than any of these previous dedicated solar radio telescopes, will dedicate some of its time to studying these events on the sun. Although I think that still needs to be worked out, whether we want to point the SKA anywhere near the sun, but that's the idea. So just to give you a flavor of what is being done with current instruments. So again, this is an example from the VLA. So firstly, the picture on the left is not a radio picture. So here we've got, again, an ultraviolet picture of the sun, with the green colors here highlighting one of these flare events. You can see material shooting upwards in this sort of vertical line here. So that would be part of that ejection upwards that happens during one of these reconnection events. The white emission that you can see way up here on the left is actually soft X-rays. So this is the hot plasma that is actually being ejected out of the sun. So you get this, so you can see the very hot million-degree gas being ejected that way. So that's shooting off into space. And here on the right, the resolution not so good for the radio. You can just about see these blue colors here, which basically are indicating that this is where the blue is where the radio emission is coming from. So this is with the VLA. So again, pretty good resolution for current instruments, but nowhere near as good as the space-based ultraviolet satellites at present for this kind of work. But you can see that there's a lot of radio emission coming from in the vicinity of where this magnetic reconnection event actually took place. So the idea in future would be to try and zero in at higher resolution and sensitivity on these kind of events. So here's another schematic to illustrate this idea of reconnection. So this is where the reconnection is occurring, and so that this will, and the arrows here are indicating the flows of accelerated charged particles. So some are accelerated down around the loops back onto the sun, and when they hit the sun, you get sort of big little eruptions that we could see earlier on. But from a radio point of view, most of the radio emission is coming this way. And so we get the electrons flying up rapidly around these loops. And it's those accelerated electrons there that are giving rise to a lot of this very short burst of radio emission. And here's the ejected sort of dense filament of gas, but there's very low density in here, so very hot, very low density. So just a note actually that, you know, one reason for studying the sun is to try and understand these kind of magnetic phenomena, because, you know, that's we're getting these really good close-up views of these magnetic phenomena, obviously on the sun, that we can't get on any other astronomical object. But many other astronomical objects do exhibit, you know, this kind of magnetic flaring behavior. So obviously stars similar to the sun, and especially actually lower mass stars, which are much more convective. The cooler surface layers, that means that the convection is much deeper down into the star. They have even stronger dynamos and very strong magnetic activity. So the very cool stars, so-called M dwarfs, they really flare a lot. So they're very magnetically active. You can also get interacting binary systems where stars are very close, and again, having that binary companion can add extra sort of dynamo power, if you like, to a star, so it will increase the magnetic activity because you've got a close binary interaction going on. I think, as was hinted at during the star formation, a lot of magnetic activity going on during star formation, giving rise to those jets, but at the same time, the twisted up fields, as illustrated in the artist's impression in the inset here, is really, you know, can really twist up magnetic fields in an accretion disk, can get twisted up and lead to these flaring activity as well. And the graph here shows real data of a flare from one of these young protostar type regions. And you can see again a big increase in the brightness of the radio flux just in a few hours. So this is another example of magnetic flaring activity. And, you know, this same situation of an accretion disk with highly magnetized with jets and everything, of course, happens in the centers of galaxies on a much bigger scale, much more energetic with the active galactic nuclei. And so, you know, there's almost certain to be magnetic flaring activity going on there as well. So studying the sun and understanding the physics there will help us to understand other areas in astrophysics. Okay, so just some more pictures here now at much lower frequencies. So now we're down in the 100 megahertz regime. This is actually from the sort of new low frequency array in Europe, the LOFAR telescope. And so low frequencies are also used a lot in the study of the sun, as well as the sort of gigahertz frequencies. So here you can see, again, a time sequence of images on the top. So showing this kind of, the circle represents the sun, but you can see that there's this eruption of hot material is leaving the sun here. And the nature of the emission is quite distinctive. And in this field, you will usually see these kind of plots, which are referred to as dynamic spectra. You saw something similar with the during the way we look at pulsar data as well. So plotting frequency of emission on the y-axis and time on the x-axis. So it's a spectrum because the y-axis is a function of frequency, and it's dynamic because it's also a function of time. And you can see, so at any given frequency, you're getting a series of pulses, but as the frequency changes, you know, the time sequence is varying here, okay, due to various physical processes. And it's, you know, it's very complex emission. And it gets more complex. So here's a sort of zoom in on at very high time and frequency resolution with LOFAR. And you can see in the inset some of the real detailed structure in here. And this is not really noise. So this is the idea that what we're seeing here are, particular frequencies being picked out to do with wave phenomena in the plasma. And so there's an awful lot of potential different types of waves in these plasmas, and getting that high time and frequency resolution allows us to study those. So this is really a kind of a laboratory for plasma physics as well. And you get potential for a lot of magnetohydrodynamic wave type phenomena. So various things associated with alphane waves and slow and fast magnetosonic waves, all the kind of phenomena that you get in the full plethora of plasma physics. And so quite often you see these oscillations. This is a time sequence again of the radio flux, and so you can see these what are called quasi-periodic oscillations. So there's some kind of period present in the emission for a while, and that was coming from this flare here. So again, the contours here indicating where the radio emission is coming from, and this is what the time sequence of that radio emission actually looks like. And so again, looking at these frequencies, you can start to understand the various wave phenomena that are occurring in the plasma. Okay. So next I want to move on to looking at the idea of what happens to these loops as they go out into space. So this brings us to the sort of related idea of coronal mass ejections, which start from these energetic flares, but then the sort of open field lines will go out into space, into the interplanetary medium, so between the Earth and the Sun, out into the solar system. So again, this is all a result of that magnetic tension being released during the reconnection event, and so these loops are then heading out into interplanetary space, which is also full of plasma, and so you get a shockwave set up, and this can lead to acceleration of charged particles. So when you get a shock wave like this, so the shock is traveling faster than the sound speed in the interplanetary medium, and so charged particles will bounce to and fro in the shock and basically get accelerated up to much faster than the thermal speeds. And so you can see this idea of superthermal electrons and ions here. So you can get quite fast particle acceleration occurring as a result of these phenomena. So here I just want to replay one of these movies of these coronal mass ejections. This is from the European SOHO satellite, taken in this special way. So you might have seen this during the Foundation lecture on the same topic. So the sun here is represented by the white circle again, but it's been covered up like with an artificial eclipse by the satellite instrument. We're just putting a little dark disk over the sun so that block out the light of the sun so that we can show up these white striations of emission here. So this is in a mostly in the optical UV range, and so what you're seeing in the white light there is the very hot million-degree coronal gas, and all the other white dots here are just stars and planets in the background. So as we place the movie, we'll see again the time variability of this coronal gas, and you can see the kind of ejections and explosions that are going on that originate on the sun. So you can see these shock waves coming out through, and it's those shock waves that will be accelerating particles in interplanetary space up to very high speeds. So just a reminder, this is an optical picture. I'll just play that again because it's always quite fascinating and slightly disturbing how energetic this is. So this is in a matter of hours, okay, that these explosions are happening. Well, eruptions is a better word than explosions. So again, all powered by the magnetic field of the sun. So let's return to some radio pictures then again of how we can use radio to trace these ejected plasma. So this is a time sequence, again, pretty fast, okay. And again, this is down at low frequencies. Again, this is from the LOFAR telescope. And so you can see this blob of gas. This will be very hot gas being ejected from the sun and moving away from the sun. So just within a couple of minutes, you know, it's already 3 times the solar radius away from where it started. So very fast moving, and you can, you know, trace that quite well at low frequencies. You see immediately here that you have to keep changing the frequency. So as the gas gets further away from the sun, the density gets lower, and therefore the frequency at which the plasma is emitting also drops. So you can see that very nicely here on this plot. This is a different type of flare, but it's the same idea. So this is one of these coronal mass ejections in the schematic here. So it's expanding over time, and so the emission is coming from the accelerated particles in the shock front here. So this is the geometry, but as it expands, then the density is getting lower, and that causes the frequency to drop of the emission. And so you can see that in this dynamic spectrum here again. So early on in time, then the emission is up here at sort of 700 megahertz and quite strong. But again, over a short space of time, 2 or 3 minutes, the frequency has dropped down to, you know, about 300 megahertz and continues to drop. Okay, so you get this characteristic dynamic spectrum, which is very common for these bursts, these radio bursts from the sun. So, you know, if you really want to study this phenomena in detail, you also need to be able to cover a wide range of frequencies simultaneously, so that you can follow these outbursts of radio emission over time, and also, you know, really understand the physics here, because the shape of this is really telling you how the density is changing with time here. So you're really kind of mapping out the process as it happens in real time. So here's an example of this idea of particle acceleration. Okay, so along the bottom is the energy of the particles. This has been sort of measured in situ by dedicated satellites orbiting the Earth. So finding out, capturing the charged particles as they hurtle past the Earth and measuring their energy spectrum. And so you can see there's a lot of particles down at the low energy end. So this is what we would call the normal sort of solar wind. So that's really, you know, associated with the sort of thermal properties at, you know, 1,000,000 Kelvin. But up here you can see everything departs from a sort of Maxwellian distribution, and so you've got a tail of very high energy particles that have been accelerated by those shock fronts, and so that's what's giving rise to a lot of these high energy particles here. And it's, you know, some of these that we have to worry about in terms of high energy particles interfering with things to do with satellites around the Earth. So I just finally want to mention another way in which radio astronomy is used to study phenomena from the sun. and this is the phenomenon called interplanetary scintillation. So here, we don't look at the sun or the plasma emitting directly at all. We are looking at just, back to astronomical sources, distant radio sources, usually extragalactic background sources like the AGN, quasars, or radio galaxies, and well, probably quasars. You need to be a point source, a strong point source. So normally from a strong point source, of course, you'd expect a steady signal of flux. But from the early days of radio astronomy, it was noticed, especially radio interferometry, it was noticed that, especially at lower frequencies, then occasionally the level of the flux from the source was varying quite rapidly and randomly. And this was, and just for a short time, then it would go back to being constant again. And so this was tracked down to being clouds of sort of denser plasma in our own solar system. And so it's associated with these outbursts of plasma from the sun, which gives at certain times, as they pass in front of the background radio source, will lead to enhanced scattering of the radio waves from the distant astronomical source as they pass through the nearby cloud of plasma. And so this is analogous to the kind of twinkling, if you like, of stars that you see in the optical when you look up at the night sky with your naked eye. So the turbulent plasma here, the different densities and temperatures have different refractive index, and so that refracts and scatters the radio waves different amounts as the turbulent cloud passes in front. So that gives rise to this time variation of the signal. And by looking at the sort of structure in here, you get an idea of the size scale of the turbulence in these clouds. So it is actually telling you quite a lot of information about that you can't really get any other way. So it tells you about very fine level structure in, basically on what scale are these clouds turbulent. If you do multiple observations, you can find out sort of instantaneously how fast the cloud is moving as well. And so you can get quite a lot of information this way. And if you can monitor multiple radio sources in the sky simultaneously, you could, build up a picture of, where these turbulent shock fronts are perhaps as one of these coronal mass ejections is heading towards the Earth. So potentially this is a way of getting an early warning that one of these eruptive events and all the fast particles are heading towards us here on the Earth, if you could monitor this scintillation in real time. So most of the satellites tell us when an eruption has happened here on the sun, so you can certainly monitor that, so that you know when the big flares have happened, but you don't necessarily know whether they're heading towards the Earth or not. And this is important, okay? So this is the big field these days of what is referred to as space weather, okay? And so this is because the Earth is in the firing line of these eruptions of magnetic plasma and fast-moving accelerated charged particles, all hurtling towards the Earth at thousands of kilometers per second. And so, what happens when they reach the Earth? Well, luckily, we have our magnetic field, which protects us from most of the harmful effects of this. If we did not have a magnetic field, it's more than likely that life on Earth would never have evolved, because all those charged particles would be raining down on the surface of the Earth, and that's very damaging to cellular life. So, we need to be thankful for our magnetic field. but sometimes these events are so strong that charged particles can work their way down through the magnetic poles. They start to spiral around the magnetic poles of the Earth, and so they can certainly reach the sort of regions where satellites are orbiting, and so sensitive electronic equipment on telecommunication satellites, etc., navigation satellites. They really don't like fast-moving charged particles that can destroy the electronics. And the big solar storms, magnetic storms, you can end up with significant sort of electrical storms reaching the surface of the Earth and knocking out power grids, etc. That's happened a few times in Canada, in the northern regions, knocking out power plants and all sorts of things. So, and obviously these days when you've got space stations with astronauts in space, then you really don't want to be outside your space station when one of these storms comes past. And so again, a lot of monitoring going on to find out if and when any of these flares are approaching the Earth. So that's the whole idea of space weather. And the more we can understand these magnetic processes that are driving all of this on the sun, then the better we will become at predicting this kind of weather, as well as the everyday weather down here on the surface. Okay, so that concludes my little pictorial tour of what radio astronomy can do for the study of the sun and associated phenomena. So hopefully you got the idea that perhaps both parts of the SKA, so the low frequency part in Australia and the mid frequency part in Africa, will be very good at addressing a whole wide range of these kind of radio phenomena associated with the sun, because you will have this combination of much bigger sensitivity. So you can go at high time resolution and pick up weak sources or individual details. And you've got that combined with high spatial resolution, because the current solar telescopes in the radio, most of them have baselines of just a few kilometers. So if you've got a very dense core in the SKA with tens of kilometers baselines, then you're going to have 10 times higher resolution at least to start to pick up much finer details. And so the aim really is to further our understanding of the intricacies and the complex physics that goes on in these magnetic reconnection events that lead to the solar flares. As those flares propagate out into space as coronal mass ejections, then we're into this realm of plasma physics, so really trying to understand how these plasmas propagate across space and the various processes, magnetic processes that go on there in terms of sort of wave phenomena. And in terms of, finally getting to a piece of astronomy that actually can affect life down here on the Earth, then as I've just indicated, so this field of space weather is very important in terms of preserving sort of astronauts and satellites in orbit around the Earth, and also extreme events that can interrupt power and telecommunications down here on the surface of the Earth. So I will stop there, and then we will kind of pick up in the next lecture this idea of these sort of solar wind and solar flares interacting with planetary magnetic fields as we start to look at the role of radio astronomy in the study of planets around other stars.